You know, the ground right beneath your feet. It feels so solid, so permanent, doesn't it? But what if I told you it has a story, a really dramatic biography that stretches back 4.6 billion years? Well, in this explainer, we're going to peel back those layers and tell the epic tale of Earth's skin, its crust.
All right, so here's our roadmap. We're going to start at the very beginning, with Earth's fiery birth. Then we'll get into the two totally different types of crust we have today. We'll uncover the great recycling machine that drives the whole system, and finally, see what this restless planet means for all of us.
So let's rewind the clock. Way, way back, 4.6 billion years ago. And I want you to forget the blue and green marble you know. Picture this. Earth was an unrecognizable, raging ball of molten rock, a world of pure fire. The timescale we're dealing with here is just mind-boggling. To give you some perspective, the entire history of humanity is just a tiny, tiny blip at the very end of this timeline. The real story of our planet's skin is written across billions of years. So how did this planet even happen? Well, it wasn't quiet. It was through this incredibly chaotic and violent process called accretion. Basically, dust and gas started clumping together, then small rocks started slamming into each other, and all of those collisions generated so much heat that everything just melted into a giant magma ocean. Now, as this molten ball started to cool, it formed a kind of initial skin, a primordial crust. But here's the thing, you will not find a single piece of it today. Why? Because it was constantly being shattered by giant asteroids and churned back into the mantle. It's a completely lost first chapter of Earth's story. Okay, so if that first crust is totally gone, what came next? Well, the answer involves not one, but two new types of crust. And we're going to start with the one that's hidden beneath the waves, a crust that is constantly being born and destroyed. This is the oceanic crust, and the best way to think of it is like a planet-sized conveyor belt. New crust is always being made at these volcanic ridges deep in the ocean as magma bubbles up from the mantle and cools. Just look at that number, 200 million years. In geologic terms, that's practically brand new. It is the absolute maximum age for any piece of the ocean floor on the entire planet. It gets born at a ridge, it travels across the ocean, and then it gets recycled back into the Earth. Now, on the complete other end of the spectrum from that geologic infant, you have the continents. These are the planet's wise old elders. This is the tertiary crust, and it's a crust that is absolutely built to last. 4.3 billion years. That's the age of the oldest single thing ever found on Earth, a tiny little zircon crystal, discovered buried deep inside a continent. It is a direct relic from our planet's infancy, a literal time capsule. And these incredibly ancient materials, they aren't just found anywhere. They're locked away in the super stable, rocky hearts of the continents, in areas we call cratons. These are the ancient foundations of our landmasses, and they act as a kind of planetary archive of deep time. So this really brings us to the fundamental difference, the whole story in a nutshell. You have the young, dense oceanic crust, which is heavy, so it gets recycled. And then you have the ancient, less dense continental crust, which is just too buoyant to sink. In the biography of Earth's skin, density is destiny. So what explains this massive difference in their age and their fate? It's all driven by a planet-wide engine of creation and destruction, an engine we call plate tectonics. And the key process in this great recycling machine is something called subduction. This is basically where a heavy, dense oceanic plate runs into another plate and is forced to dive back down into the Earth's hot mantle, where it gets melted down and, you guessed it, recycled. The whole cycle kicks off right here, in the middle of the ocean. Magma wells up, creates brand new oceanic crust, and literally pushes the seafloor apart, starting it on its journey. And that whole creation process actually creates a force called ridge push. It's one of the engines that sets these massive tectonic plates on their slow but relentless journey across the globe. So after millions of years of traveling and cooling and getting denser, that old oceanic crust finally reaches the end of the line. It hits a subduction zone, and down it goes back into the mantle, completing its life cycle. But the continental crust? Totally different story. It's just too light, too buoyant to sink. As the source material says, it's not readily destroyed by subduction. So instead of getting recycled, it just floats.
It survives for billions of years like a massive, unsinkable geological life raft.
Okay, so let's bring this enormous story into the present day. What does all this constant movement of our restless planet actually mean for us, living right here on its surface?
Well, over deep time, this drift has created a grand cycle, the assembly and breakup of huge supercontinents. I mean, the land masses we live on have repeatedly crashed together, forming giants like Pangaea, only to tear themselves apart again. It's a dance that has shaped the entire evolution of life on this planet.
And this chart just says it all. The age gap is just staggering. The oldest ocean crust is a mere 200 million years old, while the continents average around 2 billion years, with some minerals dating back almost to the very beginning. They really are like two different worlds just coexisting on the same planet.
And look, this isn't just ancient history. The slow dance of the crust has very real and sometimes violent consequences. That grinding movement is what causes earthquakes on land, and when it happens suddenly under the ocean, it can unleash devastating tsunamis. So, we'll end on this thought. The story of the crust is far from over. The plates are still moving, right now about as fast as your fingernails grow. The continents are even now on a slow-motion collision course, which leaves us with a pretty fascinating question. What will Earth's next supercontinent look like millions of years in the future?